So what we did last time was just showing you how to explain the thermal expansion phenomena, all right, and using just only a linear equation. So I hope you saw that one, and then you understood that that's equation, that's an approximation. Okay, that is not a law of nature or anything, but you try to explain the expansion due to the change of the temperature. All right, so given that explanation using just a simple equation, we can do some calculation very easily. But to sort of understand the idea of the thermal expansion, just to make sure I check your understanding one more time. So let's answer these simple questions. Two spheres are made of the same metal and have the same radius, but one is hollow and the other is solid. What do you think? Now you have a hollow one, or you can think it's like, you know, some sort of, you have some blank space inside, and then these two are taken through the same temperature increase. So which one should expand more? What do you think? So actually I have a parallel questions that I can ask you in the same sort of, it's pretty much the same manner, but different dimension. So think of it this way. If you have a hole in two-dimensional plate, let's say you have like a metal sheet, and then you have a circular hole, or it can be any kind of hole in there, and then you warm it up, what will happen to the hole? So this is the same kind of question that sort of in this same line of thinking qualitatively. All right, what do you guys think? What will happen to the solid case and the hollow case? Should expand, the whole expands. Okay, very good, very good. Okay, that seems reasonable answer. Yes, yes. Whole expand. Any alternatives? Any difference? So if I draw this figure in a different manner, if I sort of like draw a small hole in there and warm it up, would it make any difference at all? Having a large hole or having a mini tiny hole in the piece of the metal? So the answer is correct. So don't forget the key features that we talked last time was everything is coming from microscopic level. So think of it this way. The thermal expansion is due to the movement of the molecules, and then eventually they try to separate each other because the movement is just getting greater. So when you have a greater movement, it's going to try to push environment around. So everything just sort of like expanded out. So think of it a microscopic world. If you zoom it in, if you are one of those molecules around here, this is way too big already, you're never going to be able to know, is there going to be any whole million molecules away from you, right? So you don't know. So at the end, I mean, you're just shaking, and then you just like push your friends, your neighbor atoms, neighbor molecules around. So everything should get enlarged, no matter if there is a hole or not. All right. So overall, what I'm saying is you can think of this thermal expansion like a Photoshop enlarge function or something. It's like you zoom it in or you stretch the whole picture. So you can think of it this way. Once you warm it up, the whole thing will get expanded like that. The whole thing. So everything is just getting larger. Okay. All right. So that's the whole idea. So same thing up here. When it's warmed up, it's going to get larger. But because, I mean, the molecules don't know is there a hole or not, then they're going to get larger at the same amount. Even though you might be able to argue to me like, hey, Ajahn, it's impossible for these two cases to be exactly the same. Yeah, you're right. But I mean, we already tried to work around everything under first order approximation. So up to the first order approximation, you would say they are the same. But if you sort of like dive down to maybe 10 digits, then of course you might see some differences. All right, but that will be too much work for nothing. Okay, so just given that the framework of what we are doing, everything is linear, then we can say that the thermal expansion process going to give exact same results, no matter it's the solid or it's a whole case. Okay, sounds cool. All right, so think of it like a Photoshop scale, I mean, zoom in or just stretch, enlarge the whole thing. That's what it is. Okay, so let's take a look at a simple calculations using this equation. So you have an aluminum tube, 3 meter long, and as you can see, they try to provide you with a lot of digits over here just to take care of the detail changes. At 20 degrees Celsius, what is its length at 40 degrees Celsius, and what happens at 0 degrees Celsius? Okay, so this is a simple one to try, so you feel comfortable using this equation very easily. So first of all, our equation is delta L, the change of the length, starting from the alpha. This is the aluminum, so all you need to do is just look it up in the table or look it up on the net just to see what is the value of the coefficient of linear expansion of aluminum. And then you start from the initial length, 3 meters, so just put it there. You can put 40 after or not, that's up to you, that's fine. And then you do the delta T. Now this is, just want to be clear that the delta can be positive. In the first case, case A is a positive 20. The change of the temperature is 20 plus, that's increased 20 degrees. Or the change could be a negative change. So this equation can take care of the extensions or the enlargement or expansion, or it can take care of the contractions. Okay, so it works. All right, so for part A, so you just multiply by positive 20. So the delta L will be positive. For part B, it will work exactly the same, except you're going to get a contraction. So everything will shrink down a little bit by that much. All right, so that's good. All right, so it's very easy to use. It's a straightforward one that you can try using this equation anywhere, anytime. All right, but this one, they care only about the length. That's why we use only the first order equation in one-dimensional form. All right, we don't use the volume. We don't have anything. We don't have any information about the volume. So that's why we stick with the length right there. Okay, all right, try this one, guys. All right, so in general, this is supposed to be like a quiz. And I'll give you like 5 minutes to do and submit your answer. But yeah, no. All right, just do this together. So a concrete sections on a certain superhighway, few are designed to have a length of 25 meters. Now the sections are poured and cured at 10 degrees Celsius. What minimum spacing should the engineer leave between sections? All right, you guys kind of know already, right? When we saw the photo in the disastrous case in the railway case. So what they have to do is when they want to put a concrete block on the street or on the road, they have to leave some spacing between blocks and stuff just to take care of the expansion during the daytime. All right, and it turns out during the construction and everything, they do everything at 10 degrees Celsius. That's what they have. But then during the daytime, this temperature will raise to 50 degrees Celsius. They want to know what is the minimum spacing that they should leave between this. So let me call this X, or you can call delta X for now. Yeah, so let's figure out that delta X, shall we? All right, so first of all, because we know that this piece of concrete is 25 meters long at the time of the construction, at the time of the curing and everything. So this is a 25 meter long. Okay. All right, so what we want to know is just what will be the expansion when the temperature reaches 50 degrees Celsius. So the delta T is positive 40. So that's it. That's pretty straightforward. Now you can calculate the change of the length to be the alpha of the concrete times the original length times the change of the temperature. So the alpha of the concrete, actually, we had that in the table here. If you can go back and take a look at it right here. So it's 12 times 10 to the negative 6, all right, the alpha for that. So that's what we can do here. So 12 times 10 to the negative 6. All right, let me omit the unit here, so make things a little bit sort of nice and sort of like just purely number. The length originally is 25. The delta T is positive 40. That's it. So once you plug in all these numbers, the final units will be in meter. That is the change in the length. Alrighty, and that is it. In the sense that now in reality, of course, when things get hot, the concrete will expand in all directions. Because right now we care only about its length along the surface of the road. So to be fair, actually the delta L should actually split half on both sides. Agree with me? Sort of, yeah. Even though you know that the delta L is going to be this much, but in reality, it's probably going to expand on both sides. So let's think of it like it's going to expand delta L over 2 on both sides. Okay. And each piece of the concrete will do the same delta L over 2 on both sides like this. And that lead you to the minimum spacing that you need is, once again, twice of that delta L over 2, or the delta L anyway. Okay, that's fair. All right, so that means whatever the numbers that you get for the delta L, that will be your delta X, the minimum spacing that you need to leave between the concrete block. All right, so that's kind of like, all right. Wish that this kind of question shows up in the exam. All right, this is maybe too easy. All right, but at least this show you how to work on this kind of question. All right, it's a warm-up question, guys. It's a lecture number 2, so still nothing complicated at this point. All right, so just try to ease you in, right? Don't go away just yet. All right, everything's good. No questions so far. All right, try again. Next one will be a lot more fun. All right, here we go. All right, this is a more challenging one. I want you to try. All right, I'll, of course, just give a few minutes of thought, thinking how to solve this one, and then after that, then we can go through this one together. All right, so we have a liquid, has a density rho. All right, everyone still remember the density. By definition of the density is just the mass over volume. That's no big deal. Now show that the fractional change in density for a change in temperature delta T is given by that expression down there. And what does the negative sign mean? You guys want to try this? Right, I think this is a very good university physics level questions edge. Sort of like, all right, it's not number, it's not a numerical questions, and it's more like trying to do some relationship and stuff. So it's sort of like a verification type problems. So I think this is a good practice for you to try. All right, so I'll give you a couple minutes to think of this. How are you going to approach this one? All right, what do you think? All right, I don't know you like this. I mean, some of you don't like this kind of question when there's no number or anything. You don't like it. Like some of you still like want to know, like, Ajahn, which formula should I use? Okay, is it when the temperature increase, the pressure? Okay, all right, right now we still don't have the pressure just yet, because you can think of it this way, that it's a liquid at this point. So, or I mean, it could be a solid. All right, so at this point, you're probably not talking about the pressure of the material itself, but something around there. Yeah, it's pretty close. A hint will be, it has something to do with this volume. Now, even though we are not talking about the gas just yet, so we don't have pressure come into the picture, but from the formula of the density, we have the rho, and the rho linked directly to the volume of this. And everyone knows when things get hot, this thing is going to expand a bit. Yeah, all right. When things get a little bit hotter, all right, so the volume of this object or this piece of metal or this liquid in this problem is going to expand a bit, and that will change the volume. There you go. Once the volume changes, and then of course we're going to assume that the mass not going to change. So that's the idea, that at least when the volume is up, the rho is supposed to be down. At least you get an answer that why the negative is supposed to be there. The negative just saying that the change in the density rho will be in opposite direction to the change of the temperature. That makes sense. Higher the temperature, bigger the volume, larger the volume, the density will drop. So at least that part of the end, that part of the question is already get answered. Where the negative sign is for, that's it. Just to say that it's opposite direction. What is that? Yeah, here you go. Opposite direction. between the delta t and the delta rho. But how do we get to that? And as you can see from this, it's 10. The beta, the coefficient of the volume expansion is in that expression. So I'm sure it's going to be there. It's going to link to the question of, the expression of delta V is the beta V naught delta T for sure. It has to link with the thermal expansion expression that we have already learned. But how can we get to that? Well, I would say in an easy way. All right, so I'm going to show you this. I think maybe the easiest way is you already saw last time that I can go through the understanding of the expression by using either the algebra, using the approximation from the algebra, or I can do using the calculus way. That's no need any approximation because everything just infinitesimally small. So everything works well in that region. So I think I'm going to do the calculus approach here because you saw from last time, it seems to be a little bit easier, given that we all have some calculus basic. So what I'm going to do is this. So I'm going to start from the expression of the density. All right, the key is this. When you're doing calculus, you want to do the change. And whenever you want to do the change with respect to anything that is the derivative. So that's the key. In your head, you want to know what is the change in the density with respect to the volume. Does that make sense to you? That's what you're thinking. I want to know what is the change of the density with respect to the change of the volume. So what I'm doing over here is I'm just going to take the derivative of this with respect to volume on both sides. Sounds good, guys? It's cool. All right. And on your right side, you know how to do this because m is constant. So you take the derivative of 1 over v. So the derivative of 1 over v is what? Of course, it's going to be m negative 1 over v squared. You guys with me? Yeah, I can move this a little bit away. Yeah, makes sense. So negative signs comes up directly from the calculus. The reason is because it's inverse proportion. I mean, there is an inverse relationship between the v and the rho. So when you do the derivative, it's automatically have the negative sign in the front. Perfect. Calculus take care of the relationship automatically. And now I can turn this derivative expression into a differential form. So that means I can rewrite this equation to look like this. Here we go. D rho, the differential change of the rho, is going to be negative m over v squared. And then I can just move dv to my right-hand side. Sounds good? All right, Ajahn for calculus probably not going to like this. When I say move dv to the right, and that's well, this is an unofficial way, but it works all the time, so it shouldn't be a problem. All right, then. So what we have over here is now you can apply this. Remember, we had this before in the differential form as well. It looks like beta v dt. Yeah, isn't that nice? Yeah, everything goes to 0. The equation looks perfect. That's not an approximation anymore. So over here, then I can replace that dv by the beta v dt. Almost done, guys. 1v cancel right there. I am left with m over v ratio in my right hand side. That is the rho itself. So that means now my expression now looks like this. D rho equal to negative rho beta dt. And can you see now? I can get to this. And that's checked. Done. All right. So I hope by bringing in the calculus to these calculations, I think that make things easy. Plus, it's kind of like, it's good to see the relationship in a differential form. Everything infinitesimally small. So when you have something so small like that, and then you can turn the d back to the delta. So you sort of like, you zoom out, but you still keep that linear change from the differential scale there. So that's think of it like that's what we did over here. Same thing. So when you have something delta, that's big, but then when you do something super small, that's the D. The D is actually very perfect. That is when things go to 0, that's perfect. That's not an approximation. But then when you go backward from differential D back to the delta, that means there must be some approximation going on there. I don't know, I'm keep talking like back and forth between the D and the delta. I hope I'm not confusing you in any way. So it's still all right? Okay, all right. So don't forget to just like give me some, I don't know, sticker, emoticon. It's just like, hey, some signal that I'm still around. Okay, cool. All right, good. Guys, let's do one more. And this is exactly, oh, well, not exactly, but this is the level of the question that shows up in the exam. And actually, I have been posting this type of question in the exam so many times, because I think if you understand this level of problems, then I think that's good. I think that's the objectives of understanding what the thermal expansion is. All right, so guys, try this. And if you can attack this one, then I think we close the topics of thermal expansion right here. Okay, so let's read the problems together, shall we? So we have a poorly designed electric device. Has two bolts. Okay, one made with steel and the other with brass, as shown in the figure right there. All right, and almost touch each other in the interior. So they're almost there. It's 5 micron separated. When they touch, a short circuit will develop and damage the device, which is not good. If the initial gap between the ends of the bolts is 5 micron at 27 degrees Celsius. Now here comes the questions. When are they going to touch? At what temperature that these bolts will touch? So you see, the question here is not that hard. It's a direct application of the linear expansion expression, but it just adds some complexity into the problem just a little bit. All right, that's not too bad. All right, okay, you guys try this. All right, this is like a really like a quiz worthy problem, really. I should do quiz on this. All right, just kidding again. All right, so don't worry, no quiz here. Okay, if you can set up the first equation, I think that's already perfect. Right? You don't need to go through all the details, spending time doing the numerical calculation or anything. Just set up the main equation that you really want to solve. And once you get these problems, everything is good. Okay, guys got this? Not too bad, yeah? Not too bad. What is the expansion constant for both? Okay, so that's no big deal. Let's say that you will have a way to figure out the alpha for the steel and the alpha for the brass. We can look it up somewhere on the net or in the exam, it will be given, or because we're going to have like take home exam, then feel free to find your own alpha and then just plug it in. That is up to you. Well, up to the data that you got. All right, so let's say that the coefficients of thermal expansion for steel and brass are given. So what should we set up the main equation? All right, so here we go. Think of it this way. They're going to touch when the expansion closes this gap, right? But the expansions must come from the steel and the brass contributions. That's it. When I say that's it, means, of course, when temperature rises, there will be a delta L coming from the steel. Let me put the subscript S for that. And there will be an expansion coming from the brass. Let me put the B subscript for that. And that's it. The sum of these two expansions must eventually close this gap. So the key equation that we need is just delta L of the steel with the delta L from the brass eventually is going to close the gap, 5 micron. And I turn micron into 10 to negative 6 meter. Done. That is the main equation that we need to solve. And then we just apply the linear equation for the thermal expansion. So what you have here is delta L for the steel is going to be the alpha of the steel times the initial length of the steel, which is given to be, here we go, 0.01. Okay, let me just omit everything else and we'll just stick with the main equation right here. And then you want to know what is your final temperature. So let's say the T final to be at some X temperature, degrees Celsius. So that means the increase in the temperature will be X minus 27 for that. Sounds good? That is the expansion for the steel bolt. Same thing happens to the brass bolt. It's going to be alpha for the brass. The initial length of the bolt for the brass bolt is going to be 0.03. And they are going to go through the same temperature increase, X minus 27. Equate this to the 10 to the negative 6 meter, and then that's it. X will be something here. Done. Okay, this is good. All right, so I hope you see that this is not bad. And if the problem shows up just about here, I mean, this level of difficulty, you guys will be happy, I think. All right, any questions so far? You know, why is it minus 27? Oh, because they say the length that you are seeing in this figure over here is at 27 degrees Celsius. So when you want to know, when you raise the temperature up to the X degrees Celsius, the temperature change, the delta T, will be X minus 27. Does that make sense? It expands, so the temperature shouldn't increase. It expands so that. Oh, okay. All right, got it. Okay, very good. Okay. All right, so you raise the temperature. So when the temperature is increased, then you get the expansions in proportion to the delta T. And the delta T is X minus 27. Okay. All right, so that's it is done for the thermal expansion. All right, things we're gonna get, getting harder and harder. All right, but we're just going about this pace. So I think this pace is about right, you guys. Is that too slow, too fast, or is it? I think at this level is good. I'm not trying to push too much. Good. All right, great. All right, at least good pace. All right, cool. So this is good. All right, you guys just grab popcorns, coffee, donuts, whatever. It's just think of it like we hanging with each other for 2 hours. Okay. All right, guys. Things are gonna get a little bit more complicated, but I'll try. I forgot to let you know, I mean, last time that don't mind about the syllabus too much, because the key point is I'm gonna just teach you as far as the time is allowed. So our final exam will cover the material up to the day that we study for the last time or the last lecture or whatever. All right, so don't worry, I'm not going to try to push the material to be like cover everything on the syllabus. I don't care, because my philosophy is one is better than none. So if you understand something and we're going slowly, but you understand those stuff, I think it's way better than I'm trying to sort of run and then finish everything, but then you don't get anything at all. So get something from the course. I think that will be the main goal for my teaching over here. Okay, guys. So the next stop that we're going to do now, we're going to introduce you once again the state of matters, and there will be one state that we are going to deal with in particular. All right. So you guys know solids, liquids, and gas. So that's no big deal. All right. At low temperature, of course, we assume that everything will solidify and turn it into like a chunk and solid piece. And there will be some type of material that is somewhere in between. It has like change the shape, depends on the container and other stuff, that will be in the liquid phase. And when the temperature is high enough, or the conditions are perfect, or some requirements are met, then those will be in the gas phase. All right, so these are the three states of matter. Okay, one state that we're going to use mainly in this thermodynamics section is gas. The reason for this is, first, you have a law that can explain their properties really well. Liquid is tough because it's changing shape all the time. Okay, solid is kind of nice, but it doesn't have any change for you to be able to notice or learn from it very easily. So the good thing about the gas is it's changing the shape enough under some law. So you still have a way to keep track of changings, things that is changing. Then you, all right, I have an equation to track you guys, like what is the change, what have you done, on and on. But for the liquid, is the business is going to get even more difficult. All right, and the solid is so rigid that the change is going to be small, so you're not going to have a lot of examples that you can learn thermodynamics from the solid. However, thermodynamics works on all the matter states. All right, it doesn't matter which state of the matter, thermodynamics still works. But when we learn gas, that's when we have the most fun. All right, I'll show you why. All right, so we're going to stick with gas mainly, and we're going to learn a lot about this. First, we assume that the gas is an ideal gas. It's not like a real gas, because the real gas is complicated. When you say real gas is complicated, is first of all, the structure of the gas itself is not be as simple as just like a circular particle like this. No, probably you have some molecules, some crazy stuff over there. So we're going to assume that this is just a monotonic. So that means it's going to be like single atoms type molecules, or atoms actually. All right, so that means, well, there are no internal structure. All right, so the O2 is already out of the way. So the oxygen is already too complicated because you have two oxygen atoms on both sides of the molecule. So we're going to assume a simple ideal gas first. All right, and of course we're going to assume monatomic gas in the first stage. Second thing is, because we don't want them to interact so strongly, so we're going to assume that they are quite far apart. And to have them far apart, so we assume that the pressure is still quite low. But when I say low temperature, it doesn't mean it has to be super, super, super low. At room temperature, I think that's low enough already, right, for you to approximate that the gas is quite ideal. All right, so we say that the pressure is not super high, and the temperature is high. It doesn't mean that you have to be like a supernova high or something. It's just high enough for the gas to move around, and they can sort of like, stay apart from each other. So that's about where it's supposed to be. So by having this simple setup like this, you end up with an ideal gas system. All right, okay. And good thing about having an ideal gas is we assume that the atoms or molecules in this gas will not interact with each other at all. So we assume no intermolecular forces. No, I have to say no. There's no intermolecular forces. So forget about like van der Waals forces, forget about ionic bonding, forget about the covalent bonding, electrons, covalent, forget about it. We assume that it's like a single piece of particle running freely without any influence from neighbor atoms. Okay, so no lightning. What is lightning? It's like lightning strike. Or you mean light? Oh, so no light. What is that? It's something that I don't understand. All right, okay. However, you might think, well, Ajahn, but are they going to bounce? I mean, they can collide though. There are tons of collision, because we talked last time that there are million molecules in this room, for example. They're gonna knock each other all the time. But yeah, okay, that's fine. Knocking is not interacting. I mean, well, it's interacting in a way, but if we assume that the collision is still elastic, so we still allow collision to happen. But as long as you have an elastic collision, remember from the momentum back in the Newtonian days, 101. So as long as your collision is elastic, then you don't lose any energy during that collision. So I think it's fine. Collision is allowed because that is the mechanism that change the direction of the gas and make it random and everything. So that's kind of nice to have. All right. So if we agree with this setup, so we say that we are dealing with ideal gas, we have some variables that we can explain the state of the gas. So that's good. All right. So we can specify the state of the gas using the state variables along with some constant. Of course, constant has to be with us because we somehow come up with like SI system. Somebody use centimeter, somebody use liter, somebody use this. So there must be some constant to do some conversion, make things coincide. So with that state variables, you end up with this. There are tons of variables. Well, not tons, but there are many variables that can be used to describe this gas. And you probably familiar with all of these already. Pressure is good. Yeah, that's fine, Dan. Pressure is pressure. Pressure is all around. Even though you know the pressure is actually is a knocking of those molecules on the surface, right? That's a microscopic level of the pressure. And I think you learned this from fluid dynamics from last course already, pretty much. But if not, well, it's pressure. Like right now, we are at 1 atmospheric pressure, for example. All right, temperature, this we learned last time, very good. Volume is easy to do, just like width, height, length, that's fine. The number of molecules, that easy, we learned about this, we just count them, 1, 2, 3, 4, 5, 1 million, 10 millions, on and on. The number here, let me jump to this. Number of mole, this one is the one that you're familiar with. All right, so with this, I think you are in good hands. You have enough state variables that can be used to describe the gas. The two that is not so well known or you're not going to use a lot is the molar mass and the total mass. I think total mass is kind of like not very easy to use because who is going to weigh the gas? Like, what is the mass of the oxygen molecules in the room right now in kilogram? Who will do that, right? Nobody wants to do that. And same thing with the molar mass. For us, I don't think we need it because it's just a mass per mole. So if we know the number of mole, then we just multiply by the mass of one atoms, then you get the mass per mole. So I think you can pretty much ignore these two. We're not going to use this in our course, but at least it's there. Chemistry, some people in biology, maybe they still need it because they want to do some reaction calculation. They want to know how much mass is before the reaction and after, how much is missing, on and on. So I think for those purposes, then maybe they still find very useful there. But for us, as a fundamental understanding of thermodynamics, yeah, we still don't need that much. Okay, and the constant that we are in the play, we are going to see in the play of this business is Avogadro number. You already told me that you know this number before. So this is good. And now there are two more that I'm going to propose to you now. It's called the universal gas constants and the Boltzmann constant. All right, I'll show you what these are. Here we go. You guys familiar with this equation? Yes, PV equal to nRT. Cool. All right, so if you are familiar with this, that's nice. If not, it's simple. Zoom it in. That's it, guys. This is the equation that tells you the relationship of the state variable of an ideal gas. Simple as that, seriously. So if you are considering a system of an ideal gas, somehow if I know the pressure, let's say I'm in this room, for example, I know the pressure in my room, I can make a measurement of my room, what is the volume, I can calculate or I can make a measurement of the temperature in my room. Using this equation, I will be able to figure out the number of gas in the unit of mole in my room. Does that make sense to you? As simple as that. All right, so this is equation of states in the case of an ideal gas. So at least, see, that's how you need to know something about it. You have to know pressure, you have to know volume, you have to know temperature to get to the end. I mean, you have to know quite enough for you to be able to calculate the rest. But that is the relationship. And then if you change your mind, but Ajahn, I don't want to deal with the number of mole. I want to deal with the number of molecules. Okay. If you want to deal with the number of molecules, let me call those capital N. Number of molecules mean you count 1, 2, 3, 4, 5, 6, 7, 8. But everyone know that 1 mole is 6 times 0.02 approximately times 10 to the 23rd, right? Yeah, that's the number that you're familiar with, that one Avogadro number, yeah? So I'm going to call this number to be N sub A, Avogadro number. So that means you can convert between the mole and the capital N very easily by, I'm just saying this, if you take the number of molecule divided by the Avogadro number, that's how you get to the N. Cool. So that means, okay, let me zoom it out. So the number of mole is just the number of molecules divided by the Avogadro number. So that means I can replace small n with the ratio capital N over N sub A. I'll do that right now. So I turn that N into, yeah, right, capital N over capital N sub A. But then let me zoom in one more time. When you look at this, well, Ajahn, this R is the constant that shows up in this equation right here. That's a constant, all right? And we're gonna wrap up about the name a little bit. But then Avogadro number is also a constant right there because this number is fixed. So that means this ratio right here that you are looking at, the R over N, must be another constant. So I'm just gonna wrap this into another constant called the Boltzmann constant. And that's pretty much complete the whole constants in our equation of states. Okay, so conclusion, what you have here is, okay, slowly, the R right there, that's in the case that you want to use the number of mole in your equation. You use the R, which is the universal gas constants, and the value is around 8.3. Okay, if you want to pair this constant with the capital N, the number of molecule, you pair it with the Boltzmann constant. All right, and the number is around here. Actually, that's some problem. I don't remember this number either. It's not very famous. All right, but anyway, so 1.38 times 10 to the negative 23rd. Is that cool? All right, and now we understand that the constants that shows up, you can think of it like you want to just pick equation that you want to use. If you want to use, okay, let me write it like this. If you want to use the number of mole, you do this. Use the R. But if you want to use the number of molecule, the capital N, then you use the K. Right? Sometimes you might not want to use subscript B. That is fine. All right? Everyone understand this. The K is the Boltzmann constant. All right, but the main structure of this are the same. P V equal to N something T. No change. These two equations have the same structure. PV related to the temperature in this way. All right, so by having that, that means as long as you're not changing the amount of gas in your system, either the N, the number of mole, or the capital N, the number of molecules, stay fixed in your system. So I can move things around here. It means N times R is PV over T, right? Make sense? And of course, you can say this is same thing as a capital NKB. So that means when you're looking at a type of gas in a system, in a container, and this has no leaks, the gas stay fixed in the amount of gas in the system is fixed. Believe it or not, the ratio PV over T is always fixed. And that leads you to the way that you can compare two states of the gas. No matter gas changes in one state variable, the other variables has to adjust itself to make this ratio fixed all the time. PV over T stay fixed at all time. And that's pretty much conclude the introduction to the equation of state for the ideal gas. Sounds like a good one. All right, so like let's take a break right here, and then after the break I will show you how to apply these kind of equations, the equation of state, the PV over T is constant, on and on, in a couple of cases, and then we can dive further. All right, sounds cool. All right guys, so let's take 10 over here and then we'll continue on. Bam. All right, so let's give it a shot and see how simple it is to try in the simple case. When you want to just to compare the states of gas, or if you want to evaluate some state variables using ideal gas state equation, that is going to be a straightforward way as well. So let's take a look at this example. An ideal gas occupies a volume of 100 cubic centimeter. All right, so you have a volume. I can write it down here just for reference. So 100 cubic centimeter at 20 degrees Celsius. So that means you already know the temperature right there. Just note it here. And the pressure is also given. So actually you already know 3 of these variables. So that's very nice. Okay. All right. So let me count 1, 2, 3, 4, 5. So let me put 10 to the 5th right there, Pascal. There you go. All right. So there's a question comes in. Yep. All right. That's a very good question. Very good. So they want to determine the number of mole. So they want to know the small n right there. Okay. And also find the number of molecules. So that's a capital N. So I hope this will clear things up a little bit among the N and the capital N. All right. So your question is perfect. Actually, this is the way to use this equation. All right. The PV equal to nRT. You need to pick a unit system to use and make sure that you use it correctly. If we stick with the SI system, the unit of the P will be Pascal. So that's just already good. That's nice right there. The volume need to be in cubic meter. All right, so that is not. So you just need to convert that to cubic meter. And the way to do this, I don't know, we discussed this in the past. I don't know how I don't know how you do it, but this is what I'm doing all the time is just I'm going to treat the centi, the C, to be just a number. So my centi is 10 to the negative 2. Here we go. Let me write it like this. Can you see that? All right. So for those of you that sort of like confused about unit conversion, might be able to use this way of thinking. I look at the centi to be just a number right here. All right. So when you have a centimeter cubed, so that is a 10 to the negative 2 cubed. So that means it's going to be 110 to the negative 6 meter. See that? All right. And then now you can use that 10 to the negative 6 and stick it with the 100 in the front. And you already have the cubic meter units. Is that good? All right. So I hope this helped for those of you that still sort of like using the techniques of like from small to big, you divide, from big to small, you multiply. I don't know. I don't remember. All right. But that's how I'm doing it. And it sort of like you will see in the future, actually, by doing this, you can manipulate the units very easily. All right. You can make it, scale it up, scale it down, up to you. All right. So the temperature right here has, we already discussed this, the absolute temperature scale. So most of the equation that we're going to use, we'll always use Kelvin scale all the time. All right. But of course, there will be sometimes that you only deal with the change of the temperature. So if you only change the T, it doesn't really matter you are in K or in Celsius. You get the same amount of change because the resolution of the Kelvin scale and the Celsius scale are the same. So the delta T will be the same in both scales. All right, so that's what it is. But for us, for this equation, you need to take the temperature to be in Kelvin scale, and that needs to be converted as well. We just add 273 to it to make it a Kelvin. All right, and that's it, guys. So once you convert everything, then your equation will look like this: 10 to the 5th, that's already in Pascal. The V is 100 times 10 to the negative 6 cubic meter. That's perfect. And that's what you want to figure out. The R is 8.31 approximately. So let me omit the unit here just to save some space here. And it's 293 Kelvin. There you go. All right. And this allow you to calculate N. Done. Cool. All right. And of course, if you say, but Ajahn, I want the capital N, I want the number of molecule. On the left-hand side, looks exactly the same. Okay, that's the P, the V, and you just pair this with the capital N, and then you plug in the Boltzmann constant instead. That's all. So you just go back and you just use the K right here instead of the R. So it's going to be around 1.38 times 10 to the negative 23rd. And then you do same temperature right there. That's it. You're done. And that allows you to calculate the capital N. Okay. Or another method, if you really like, because of Ajahn, because we have already figured out the number of mole, you can actually jump right into capital N by knowing that the number of molecules is just a number of mole multiplied by the Avogadro number. That will be sort of like, that's good as well. But this just to show you in case that you want to go straight from the state variables directly into the capital N using the equation of states. But if you know either one of these two N's, then you can convert between them easily by using Avogadro number. Cool. All right. And of course, all right, this is too easy. All right, this is not the business that we are in. All right, don't worry. All right. All right, this is just like warm up question. All right, next one. All right, any questions? All right, okay, good. All right, next. So everyone try this. Pure helium gas is admitted into a tank containing a moving piston. Now here we go. So now you have things that can change now. All right, so let me draw like a piston can be moved a little bit here. All right, so that means the volume of this whole thing can be changed and all the stuff. The initial volume, pressure, and temperature of the gas. So you put the gas in here. Okay, and then you know the initial states of the gas in this tank right there. And perfect over, they give you everything pretty much. Right here, volume, pressure, temperature, volume, pressure, temperature, nice. If the volume is decreased to a new value, the pressure is increased to a new value, what is the final temperature? So you see the kind of question that is supposed to be. All right, with this one, you don't need to get down and dirty with the numbers and everything, but at least you know the type of question that you're going to face. So over here, you can put a subscript there, 111, just to say, hey, that is your first state or your initial state. That is right there. All right, and after the change, you might be able to just call this a new volume, that's a V sub 2. And then the new pressure, you can call it the P sub 2. And then you want to figure out what is going to be your new temperature. This is what it means by comparing between two states of the same amount of gas in the system. Makes sense? All right, so the amount of gas does not change. It only changes either the volume, the pressure, the temperature. But because you pretty much knows everything, you can say that the PV over T stays fixed at all times when the amount of gas does not change. So you can say P1 V1 over T1 equal to P2 V2 over T2. I think you did this in chemistry, I guess. It's like, you know, P1 V1 over T1 equal to P2 V2 over T2. All right, so this is it. And then all you need to do is just plug in the number. The only unknown in this equation is just the T2. The good thing about this equation is you don't need to convert every unit as long as you're using the same unit on both sides. You see what I'm saying here? So for example, if you look at the pressure over here is 200, it's a kilopascal. And down here is also in the kilopascal. So you don't have to take time to convert kilopascal to Pascal because they're both in kilopascal. So just plug it in right away. It's good. When you look at the volume, is already in cubic meter. And this is also in cubic meter. It's already perfect. Use it. Look at the temperature. Wow, it's in Kelvin already. So good. You don't even have to change anything. Just plug it in and you're done. So is this good? All right. I think this is simple enough. All right. Let's plug in just just to share, just for clarity and everything. So it's going to be 200. So let me put it just the number in there. 15 times 10 to the negative 3 over 300. That is the initial state. The final state, the pressure is 350. All right, same unit is good. The new volume is 10 times 10 to the negative 3. And the temperature, that's what you want to figure out. Done. All right, and we will do more and more of this, all right, in a more complicated scenario. But for now, this is just to showcase how to use this relationship right here. Cool. Keep going. All right, no questions, I hope. All right. Now, the stuff that is going to sort of like make it a little bit more fun is once you know that you have a system that we can deal with, now we're going to get to the dynamics of it. And to get to it, we need something to transfer. And the first thing that we're going to learn today is about heat. You guys familiar with this word so much, heat. All right. And it turns out heat is what we need in thermodynamics. And it turns out it doesn't show up before in Newtonian physics. It's this dude right here, is heat. Now I would like to introduce this topic by showing you this word and how do you feel about this. If I write down the word heat energy, give me some comments, guys. จะมีไหมเนี่ย How do you feel about this word? Heat energy. Oh, I need to do something with my hair. It's just too long. Thailand. Very good. I like that. Yeah, very good. Nice. That's good. Great. So it means you kind of know what this means. All right. What about the rest, guys? Any comments? So the thing is, it's like the translation in Thai is bad because heat in Thai is mean ความร้อน yeah. But then when you say heat energy, it sounds all right in Thai when you say พลังงานความร้อน yeah. But in sort of like in science and in physics, actually these two are illegal. I mean, this combination is illegal. It doesn't work. So first of all, I would like to open up these topics because this is not the word for it. Of course, in English, you can have a thermal. So thermal say is related to heat somehow or related to temperature, related to temperature change, all this stuff. All right, and that is the พลังงานความร้อน that is proper thermal energy. But heat is a standalone word right now. And it has the energy built into it already. So the word heat already means energy, but it's not just an energy in an object. It's an energy transfer. That is the key, guys. The take-home message today is heat is energy transfer. Seriously, this is big. This word is big. So that means every time that we talk about heat, there must be some flow. It's a flow, it's a transfer. So it has to move from one to the other, from hot to cold, everyone knows that. Or if you want to go reverse, like air conditioner, you can go from cold to hot. But whatever is going, it has to go. It has to flow. All right. So heat is not an energy contained inside a body. It's not. All right. I just want to emphasize this one. We cannot use the word heat. So that's why heat energy is not there. Okay. If you would like to talk about my total thermal energy in my body, there is the word for it. And this is another big term that we're going to use in thermodynamics. It's called internal energy. That is the word reserved for the thermal energy in an object. All right, we will learn more about this next time. But for now, let's focus on heat. When we talk about heat, all right, it's energy, but it's an energy flow. But people familiar with energy quite well. For example, if we talk about calorie, yeah, it seems like all right. Even in food calorie, it's actually is very familiar. All right. And you probably have learned this stuff maybe in middle schools already when you sort of study science or the stuff that you say that, hey, 1 calorie is the amount of energy that you want to raise 1 gram, 1 gram of water by 1 degree Celsius. Does that make sense? So as you can see, that is the amount of energy that you have to give to the water to raise the temperature of a gram of water 1 degree Celsius. You have to give. You have to have an energy flow. You have to provide the energy. That's why we call it the heat. Make sense? All right, but once the water receives the energy, it stores the energy in itself. It has a higher energy because you provide some energy to it through heat. The energy of the water, we call it internal energy. All right, so I hope you are clear between the heat and the energy. They are not the same, of course. All right. And because we study water heavily in the first phase of understanding physics of heat and other stuff, so these units stick around until today. And 1 calorie is in SI system 4.2 joules. All right, cool. No big deal. Now, the thing is, James Joule, yeah, the one that we use the units for the energy, he was the one who did the first experiment that showcased that heat is actually related to energy in the mechanical world. So actually this is like a diagram showing his first sort of like a display of, hey guys, I can convert potential energy. Here we go. This is an MGH. And I can use that MGH to warm up the water. That was like a wow, wow, wow moment right there. All right, next time I'm gonna have like some sound effects here so it won't get too quiet. But anyway, the point is James Joule was the one who showcased using his big, like huge experiment. He has like a super huge mass, and then he just dropped that mass from some height, and then he measured the temperature changes of a tank of water. And it turns out they are pretty much the same. So he was the one who's saying that, hey, they are pretty much the same. No matter you talk about energy in mechanical world or you talk about the energy in the thermal world that you name heat. Okay, so that's what it is. All right. But for us, I think that's kind of well known at this point. All right. And this one, just before we pass this topics over here, the calorie that you saw in the food packaging, that is not the same calorie that you use for like 4.2 joules right there, because it's a big cal right there. There's a capital C in the front. So actually that's already 1,000. It's a kilocalorie right there. All right, so you have to notice a little bit, is that like a capital C in the front or not? All right. Okay, so there was a question, same logic, that you can slap a chicken to cook it. Yes, correct, but it's not enough. The energy to get to the chicken, probably not enough. But yeah, you can raise some energy to it. Yeah. That's cool. All right. So, all right, that's a food calorie right there, guys. Okay, but I think in UK, or not only UK, I think maybe in Europe, I think overall, they use obvious notation right there. So that's good. That's kind of nice. Yeah, so in EU, I think they use like kilojoule and kilocalorie, obviously on the nutrition level. So that's going to be like no ambiguity there. Don't need to convert any units. Right? But for us, I don't know. There's a couple of levels standards that you can probably notice in the supermarket. All right, just check them out. Okay. All right. So here comes the thing. All right. Toward the end of today's lecture, I'm going to show you this. And I think maybe the logic is pretty simple. If you want to raise the energy of a substance, okay, you have to provide some energy. So at least you kind of know, because we already learned about the temperature, it's linked directly to the kinetic energy of the gas. So that means if you want to have a higher temperature, means you need higher kinetic energy in your system, correct? To get more energy, you need some energy to transfer to you. So this is the reason why you need some heat. If I want to warm up my body, that means my body has to have at a higher level of energy. some energy has to flow into me. So this means I need to heat myself up. And that is the energy transfer into me. So I can name that heat transfer to be Q. So we usually use Q for the heat right there. That's the heat. And everyone knows that once you receive the heat, then the temperature will rise. And that is the linear relationship between the heat flow and the raise in the temperature, delta T. The constant in the front will give you the ability for that to store energy. And we name that specific heat. Or, I mean, for now, we don't do specific yet. So we call this the heat capacity. Heat capacity. Okay, think of it this way, guys. The reason the C is called heat capacity because of this. If you have C that is so big, I mean, I just write it big just to showcase this. You have like a substance that has a very high heat capacity. Then you give the amount of heat to this substance that has a so super big heat capacity. What will happen to the delta T? Of course, the delta T will be small, guys. You guys with me? So I'll give you like a scaling picture of this. But if you give the same amount of heat to another material that has a small heat capacity, well, of course, Ajahn, the delta T will be big. The reason for that is because this equation gives you a product between the heat capacity and the change of the temperature. If something is very good at storing energy, the change in the temperature will be small, given the same amount of heat. Does that make sense to you? Okay. All right. If that's not make sense to you, answer this question. I thought I have an image here, but I think maybe that slide was taken out. When you go to the beach, let's say at noon, all right, you have the sand on the beach and the water in the sea or whatever. Which one between sand and water has a higher heat capacity? Just comparing between these two substances. Water, very good, very good, very good. Any other selections? Sand is hotter, perfect. See, that is my point. Only single answer is enough for me. That's my point. You guys can experience, I mean, think about it. The water is not that hot, but the sand is hot. But it's receive the same amount of energy from the sun. So that is an indicator that actually the sand has a lower heat capacity. Make sense? All right. And water has a high heat capacity because it can store a lot of energy in itself. So it shows up as a small change of the temperature. All right. That's what it is by heat capacity. All I get about this, 1 liter will take a long time to cool down in my fridge. Yes, because actually water is a huge heat capacity material. And actually, well, we have to thank water because water regulates thermal stuff in our on Earth, actually, at least. There's a water stream flow in the ocean there, take the hot water up to the North Pole or the stuff. I mean, there's some regulation going on. So water is huge. The heat capacity of water is big. Yeah. Can we use water as insulator? Well, it's kind of, you can insulate quite well because if you stay behind the water, you can stay cool pretty long. Yeah, you can. Yeah, definitely. Water cool PC. Yeah, that works. Works pretty well. So water is pretty good. Yeah, it can absorb a lot of heat. Yeah. All right. That's the logic right there. So in reality, to use the capital C to represent the heat capacity of an object is cumbersome to use and is inconvenience because, I mean, you might bring in just like a gram of water. I bring in like a liter of water. Somebody will bring in a tank of water, but they're all water. All water should have the same characteristic of the heat capacity, right? But because I bring only 1 gram, my heat capacity will be small, of course, in comparison to a guy that bring in like a tank of water. So instead of talking about the heat capacity of that object, it's easier to talk about the heat capacity of specific types of material. And then you multiply by the mass later, how much you bring in. For example, for water, you say, hey, no matter what water in this world or this universe, it will have this much heat capacity per kilogram. So you define something we name specific heat. The reason it's specific is because it's heat capacity per kilogram. It's specific just for 1 kilogram. So you know that if you bring in a kilogram of water, the heat capacity of that 1 kilogram water will be around that 4,100 joules, something like that. Okay, and then you bring in 2 kilograms, you bring in 5 kilograms, you bring in 1,000 kilograms, or you bring in m kilogram. You just multiply the mass by that specific heat to bring back that heat capacity of that object. And that leads you to, I think, the equation that you're familiar with, Q equal to mc delta T. Cool? All right, and then from now on, all you need to know about an object is what is the mass of that object and what kind of substance that made up of that object. Regardless of any impurity, that's advanced stuff. Of course, if you take an impurity into account, then that is not a pure water anymore. Right? So let's say, you know, you put some salt into it, maybe. So the specific heat will change. Yeah, definitely. So this table will give you like a 100% no contaminations of the stuff of water. Yeah, but of course, impurity will change things quite a bit. Yeah. All right, that's a good question actually. Okay, cool. So this table will give you like a list of like well-known substance and their specific heat. And as you can see from this table, yeah, see that? Water is like, wow, it's like 4,000 in comparison to metal, which one is kind of easy to see. Maybe you can see copper, yeah, gold, maybe. So that's why metal is so easy to raise the temperature and it's so easy to cool down because the specific heat is kind of low. Okay, and glass is somewhere in between. But no matter what you do in here, even wood, alcohol, nothing is big comparing to water. So that's why water is pretty big heat capacity substance. Yeah. All right. So I hope this is clear from the table that water is good stuff. Good to have. All right. Cool. So with that in mind, oh, I have the figure is down here is smaller. All right. So I think that's checked. So over here, sand has a smaller specific heat. All right. Cool. Due to the temperature change, that's obvious. So that's like evidence showing that the sand should have a smaller C. All right, so let's take a look at a quick example, a simple one. A temperature of a silver bar rises by 10 degrees Celsius when it absorbs 1.24 kilojoule of heat. All right, now the mass of the bar is 525 grams. Determine the specific heat of silver. All right, so this one is straightforward application of this equation. Q equal to mc delta T. All right, and all the information is already given. 10 degrees Celsius change, that is your delta T already. And as we already discussed, it doesn't matter it's in Kelvin or it's in Celsius, the delta T will be exactly the same. This amount of heat, that is your Q, and then you can turn it into an SI system a little bit. Kilo is 10 to the third power right there. And I just leave the joule to be the final units. Okay, so I just treat K as a number again. Now the mass of the bar is 525 grams. So this one is going to be your mass, but then because we want everything in SI system, you can turn it into kilogram by divided by 1,000. All right, and I just want to emphasize my point right here. The way that I do that to turn this into a kilo is I multiply by the K divided by the K. Does that make sense to you? And then I just keep my kilogram to be my final units. And then I bring that K, plug it in with the 525. So that's why I have to divide it by K, and K is equal to 1,000. So I ended up with 0.525 kilogram. So that's my point of treating the prefix to be just in number, right? You can manipulate, it's just like number, multiply and divide out. So you're doing nothing, you divide it by, you multiply by k, divided by k, it's just you multiply by 1, but you leave the upper k to the g, take the lower k, divide out that 525, something like this. All right, that's it, guys. Once you have all three, then you can figure out the specific heat of that silver. It's just going to be Q over M delta T. Plug in all the numbers and you're done. All right, too easy, of course. All right, this is the second lecture. I don't want to scare you off yet. All right, next. All right, this is obvious. This is more interesting, actually, guys. All right. A water heater is operated by solar power. I don't know any of you use solar panel yet, but it's, I think, good stuff. Yeah, would love to have one. All right. If the solar collector has an area of 6 square meters and the intensity delivered by sunlight is 550 watt per square meter, I think this number is pretty good, right? Not too bad. This is pretty close to a real life number. How long does it take to increase the temperature of a cubic meter of water from 20 degrees Celsius to 60 degrees Celsius? All right, so this is a very good question. I love this one because it's sort of realistic that you have solar panel, try to convert the energy from the sun, okay, and then they say you have 6 square meters of this, but because the sun can give you 550 watts per square meter. You remember the watt, right? The W is just the energy per unit time, right? It's a power. So if you remember this one, power is work over time. All right, good. So that means this will generate the total power of 550 times 6 watts. You guys with me? Because you have 6 square meter panel. So each square meter, you can collect power from the sun to be 550. So the total power output from your solar panel will be 550 times 6. Here we go. Now you want to raise the temperature of a cubic meter of water. So now you want to know how much energy needs to be transferred to the water to raise the temperature of the water of mass M with the specific heat of water. Okay, let me put the subscript right there, C of water. And then you do the change of the temperature, delta T. Okay, looks good. And how you're going to get that heat is going to come from the power from the solar panel. But because the power is just the energy per unit time, but the energy that we are talking right now is that amount of heat that you want to transfer to the water. So that amount of energy or the work done or whatever in mechanics is just the energy that we want to transfer to the water. So we're going to name that W to be the Q divided by delta T. You guys with me so far? All right, so that means the amount of energy transfer that you can transfer from the panel to the water is going to be 550 times 6 times delta T. So the time interval is already built into the Q. I can plug this into here. All right, let's give it a shot. So this is the energy received from the panel. Yeah, equal to the mass of a cubic meter of water. What is the mass of a cubic meter of water, guys? How many kilograms of that? Almost done. You have a cubic meter of water. What is the mass of that? You guys still with me? A cubic meter of water. All right, don't forget, guys, this is huge. Even though it looks not huge, but it's water, right? It's like a 1 meter long, 1 meter high, 1 meter deep. It turns out it's 1,000 kilograms. Is a ton, is 1 ton of water. It's huge. All right, so that's why it takes, well, a lot of stuff to hold water in a pool. So it takes a lot of heavy construction right there. Okay, so the C of water, you can look it up in the table. Let's say we can approximate to be like 40 to 100, about so. And then the delta T that we're going to go is just from 20 to 60. So that will be 40 degrees Celsius. I just put it there. All right, so I omitted the units a little bit to save some space. And that's it. From here, you can approximate or you can calculate the amount of time you have to spend. And the answer will be in the unit of second. And then if you want to convert second to minutes, to hours, to day, that's up to you. All right, but I think you will see that it takes a long time because to raise the temperature of a cubic meter of water for 40 degrees Celsius, that takes a lot of energy. Yeah, so usually at this point, you probably don't want to use solar panel energy to, I don't know, warm up the water, do the hot bath or anything like that. So the delta T is always in second. Yeah, because we keep everything is in the SI system. So the final unit of time will be in second. Yes. All right. Oh, you got some number. Great. Thank you. All right. I'll trust you. I trust you. I'll take that number. I'm very bad at number. All right. So if you want, you can divide it by 60 to get to minutes. And then you can divide it by 3600 to get to hours. All right. That's a long time, actually. Right? It takes hours to warm up a cubic meter of water. All right. So we have to wait more, or you need larger solar panel if you want to do like a hot bath or something like that. All right, guys. Very good. All right. So, and the last stuff that I want to sort of talk about it and just leave it there, just like it's the same thing. We just try to leave an open question. So next time we can discuss this. There is another shot in the change of the energy of a substance. It turns out if you keep giving the energy, transfer energy to the substance will change the temperature. Of course, it's getting hotter, getting hotter, getting hotter. It's no big deal. Q to MC, Q equal to MC delta T all the time. But then there will be a point where you hit something that we call the phase transition. Whoa. All right, so this is so obvious, right? The phase transition, that's when you're familiar from water, for example. If you keep warming up the water, eventually it's going to vaporize. Or if you start from an ice cube and then you warm it up, eventually it's going to melt and turns it into a liquid. During the melting process or the vaporization process, that we call it the phase transition. Yeah, makes sense? But the problem is this, during that phase transition, because you do the transition in phase, you need some energy anyway. But because that energy needs to be used for the transition, then you won't see the temperature change anymore during this transition phase. Does that make sense? All right, so that's why back in the historical day, they call this the latent heat. It's latent because it's meant like hidden heat. It's hidden from you by not showing as a temperature change. So the latent heat is happening when you're hitting a transition temperature. To be able to do the full transition, you need to complete the whole process. And the amount of heat that needed to complete the whole transition process, we call it the latent heat of that transition. The latent heat, we use the L for it. Okay, make sense? So for example, if you want to go from solid to liquid, we call it the fusion. If you want to go from liquid to solid, that is a solidification. Of course, if you go backward, if you want to go from liquid to gas, that is the vaporization. And if you want to go from gas down to liquid, that is the condensation. All right, but you can go back and forth, but during that phase transition, you need that latent heat for that transition. Okay, and we're doing the same thing as a concept of the specific heat. This is being defined per kilogram. That's for simplicity, because the water will have the same latent heat no matter which water you're talking about. So it depends on how much water you bring in. So you just multiply by M in the front. So the latent heat is the energy that required to change the phase per kilogram. That's what it is. All right, so that's it. So this table will give you the list of a well-known substance and their latent heat. Okay, let's look at water because we're familiar with water. So right there, water. So the melting point we know is melt at 0 degrees Celsius, and it required per kilogram this much energy, 3.33 times 10 to the fifth joule to melt a kilogram of water. Or if you want to freeze the water, a kilogram of water need to be taken out the energy of this much. You want to take the energy out from the liquid water this much to turn it into a solid water. Does that make sense? All right. Same thing over here. At 100 degrees Celsius, if you want to vaporize a kilogram of water into a gas water, then you need to give it 2.26 times 10 to the 6. That is your latent heat of vaporization. On the other hand, if you already have a vapor and you want to condense them down into a liquid water, that vapor water need to give off, let go of the energy of this much to have them turn it into a liquid water. Perfect. All right, so I think that's easy to understand concepts of the latent heat. And everything only happens at the temperature, at the transition temperature. All right, so last slide of the day, guys. This is it. This is the grand sort of like big picture of what is going on. If you start from like super cold, deep frozen ice, -30 ice, and then you keep energy transfer to this ice. Let's just sort of transfer the energy to it. So the ice will get warmer and warmer. Okay, let me highlight that a little bit. So it get warmer and warmer until it hits 0. That is your transition temperature. So then you won't see any temperature change anymore, but the ice will start to melt. So during that time, you have the mixture between ice and water until you completely melt the ice. Now everything will be in liquid form. That energy will be used to raise the temperature of the water again. So it's getting hotter. Q equal to MC delta T right there. Once it hits 100, then it starts vaporization process. So over here, it will be no show as a temperature change until you have to wait for the vaporization to complete. Then you're going to see the rise of the temperature one more time. So what I can say is this is the ML section over here. Okay, that is for the fusion process, or this is for the vaporization process. And then during the temperature change, it will be the MC delta T portion. There you go. MC delta T, capital T, sorry. I was just small t, we reserve it for time. There you go. There you go. All right. All right. And I hope you see the sort of the grand picture over here. And then next time we can practice a little bit of this and right into the business of heat a little bit further. Sounds good? All right. Very cool, guys. I think that is it for today. Thank you for sticking around. See you all right, I hope. Okay, guys. Any questions? All right. Thank you. All right. All right. See you on Monday. Yeah. Okay. Thank you, crab.